Alright, welcome back to the second part of our projectile motion worksheet problems. Here we're working on our Canon projectile motion worksheet problems, which involve what are known as two-component projectile motion problems. Two-component. And why it's called two components is now we're no longer only dealing with our horizontal direction of velocity initial, we're also dealing with our vertical, that's supposed to be a vertical arrow velocity component in order to start this problem. When we deal with both of those, instead of getting something like this type of motion where it's falling off a cliff, we instead get a motion where it comes up in an arcing motion and comes back down to earth. So let's go ahead and let's dive right in. A cannonball is launched with an exit velocity. Okay, this exit velocity, again, we call this exit velocity to differentiate from our horizontal initial velocity or our vertical initial velocity. When I talk about exit velocity, I'm talking about the velocity at which a projectile leaves either from a cannon, from a gun, from your arm, whatever. But the exit velocity is this component that's both in the horizontal and vertical direction. Okay, and what makes up the exit velocity is initial velocity in the horizontal direction and an initial velocity in the vertical. And in this case, our exit velocity is 23 meters per second. And it leaves at an angle of 15 degrees. Okay, if the cannonball reaches a maximum height or a distance in the vertical of 1.76, we want to find out how long, so we want to solve for our time that the projectile was in the air for, and we want to solve for how far it will land away from the base of the cannon. So these are two things that we want to solve for. So again, just like the other problems, I want to write down my equations that I'm going to use. So I have distance in the horizontal equals velocity in the horizontal times time. I have distance in the vertical, but now I have an initial velocity in the vertical direction, so I have to include that. VI times t plus the 1/2 at squared. And lastly, don't forget when we're dealing with two-component projectile motion, we have a third equation, which is my velocity final in the vertical equals velocity initial in the vertical plus acceleration times time. Okay, so don't forget about that third equation. So the first thing I like to do if I'm given this exit velocity over here, let's just go ahead and let's use our trig to solve for the other two sides of this triangle. So as we should know, this side for the vertical direction is going to be my opposite side, and this side for the horizontal should be my adjacent side. So if I want to solve for my vertical velocity, I'm going to use sine of my SOHCAHTOA. Okay, here's my SOHCAHTOA. So I have my hypotenuse, and I want to solve for my opposite side. I'm going to use my sine function. So I'll do sine of my angle, which is 15 degrees, is equal to my opposite side, which is my initial velocity in the vertical, divided by my hypotenuse, which is 23 meters per second. And in order to solve this, I just multiply 23 meters per second to both sides in order to cancel it from this side to get my initial vertical velocity by itself. And then I'll multiply it to this other side. And so to solve for this initial vertical velocity, I'll take 23 times sine of 15. And remember, when we're doing this, we're dealing with degrees, so your calculator needs to be in degrees. When I do this, I get an answer of my velocity initial in the vertical. Let me rewrite that. That was terrible. Initial in the vertical equals 6 meters per second. So that's my vertical initial. And when I solve my horizontal, it's the adjacent and the hypotenuse. We could also use tangent, but I just like to use cosine because it allows us to have our variable on top, which instead of doing one easy conversion by multiplying 23 to both sides, it would make us have to do two. So let's just avoid that and let's use cosine. So cosine of my angle, which is 15 degrees, is equal to my velocity initial horizontal over my hypotenuse, which is 23. So I can multiply both sides by 23. And when I do that, 23 times cosine of 15 degrees equals 22.2. So I got my initial vertical, my initial horizontal equals 22.2 meters per second. And there we go. Okay, now I can start plugging some of these values into my equations. Okay, the first thing that we're going to solve for is how long, the time. Okay, so when I do this, okay, I'm just going to go down the list of my equations and see what I can plug in, see which one I can use. So do I know my distance horizontal? No. Do I know my initial vertical or my initial horizontal velocity? That should be horizontal. Horizontal. This pen sucks. I do know that, but I don't know my time, so I can't use that first equation. So let's look at the second equation. Do I know my vertical distance? Yes. Do I know my vertical initial velocity? Yes. Do I know my acceleration? Yes. So can I solve for time? I can solve for time, but we'll see that this one's not the choice that I want to choose. Okay? If I look at this next one, it asks if I have my final vertical velocity, which I do, but the one that I want to use isn't the final. It's not the one down here. I want to use the one at the very peak, because something that's unique about the peak is that the vertical velocity at the peak of this is 0. And it helps us because we can split this into two problems, and then I can solve for either this first half or I can solve for this second half. In this case, we're going to solve for the first half, and then we're going to multiply it by 2 to get our time. The reason that I'm going to use this last equation instead of the second equation is because the way that the second equation is set up, I have time here, and then I also have time squared, which when we go to solve this is going to be a quadratic equation. So we're going to have to go through our quadratic formula in order to use that, which we don't want to do when we can use this last equation, and it'll get us the same answer in a shorter amount of time. So my vertical initial velocity we just calculated, which is 6 meters per second, plus my acceleration, which is negative 9.8, times time. So I can rewrite this to solve for time. First step I'm going to do is subtract 6 from both sides. So I get negative 6 equals negative 9.8 times time. And then I can divide negative 9.8 from both sides. And when I do that, the time that I get is going to be negative 6 times negative 9.8. It should get us a positive answer. Whoops, I multiplied mine. Divided by negative 9.8. Should get us a positive 0.61 seconds. Now we need to stop and we need to think. That's the time that it takes to get to a final velocity of 0, which is the top of this. Okay, so that's the time that it takes to get from where it's released to the very top, not the entire motion. So we need to remember to multiply this answer by 2. So when we do that, we get that our total time equals 1.22 seconds. That's our total time that this projectile is in the air for. Now, once I have that, again, just like my other practice problems worksheet, the time in my vertical direction is the same as my time in my horizontal. So I can plug that into here, and I can solve for my distance in the horizontal. When I do that, I get my distance in the horizontal is equal to my velocity initial in the horizontal, which we calculated as 22.2 meters per second, times the total time, which is 1.22 seconds. And when I do that, 22.2 times 1.22 gets me a vertical or horizontal distance of 27 meters. So DH equals 27 meters. All right, 0.61 times 2. Yep. Okay, so that's my answer for part 1. Moving on to part 2, a Nerf gun fires a Nerf dart at 5 meters per second. Okay, that's going to be my exit velocity. Remember that's my exit velocity. And it's launched at an angle of 45 degrees. Okay, whenever we see 45 degrees, we should be getting happy because 45 degrees indicates that we have a 45, 45, 90 right triangle. Okay, a 45, 45, 90 right triangle indicates that my base is going to be the exact same as my height. So we only have to do one calculation for this. If the Nerf bullet is in the air for 7 seconds, we want to find the max vertical height and the horizontal that the bullet will reach in its projectile motion. So again, I have my 3 equations. DH equals VH times time. dV equals VIV times time plus 1/2 AT squared. And VFV equals VI equals VIV plus AT. So we have 5 meters per second here at 45 degrees. That's seconds. So in order to solve this, I can either use sine or cosine because I'm looking for my opposite or my adjacent. And whichever one I get, it's going to be the same for either one. If you don't believe me, you can try it yourself. I'm just going to use sine. So sine of my angle is 45 is equal to my opposite side, which in this case is going to be my vertical initial velocity, divided by my hypotenuse, which is 5 meters per second. Solve this by multiplying both sides by 5. Goes away on that side. And when I solve this, I take sine of 45 times 5 gets me 3.5 meters per second. So my initial vertical is equal to my initial horizontal because it's a 45, 45, 90 right triangle, which they are both equal to 3.5 meters per second. Okay. So now we have time and we have our initial horizontal velocity, so I can use this first equation. So dH equals VH, which is 3.5 meters per second, times time, which is 7 seconds. So my distance in the horizontal, 3.5 times 7, is 24.5 meters. So there's one of the 2 answers that I'm looking for. The next one I'm going to need to use the second equation. So my vertical distance is equal to my initial vertical velocity, which is 3.5 meters per second, times my time, 7 seconds, plus 1/2 my acceleration, which is negative 9.8, and that's meters per second squared. I just didn't write it off. Times 7 seconds squared. So when I do this, 7 squared should give me 49 times negative 9.8 times 0.5 plus 3.5 times 7 gets me negative 215.6. 215.6. And again, you might be thinking, why is it negative? Well, it's because it's a reference, okay? And we're referencing from where this height is from. So if I follow this kind of trajectory, at the max height, it's going to be 215.6 meters, like above my reference point. So when we talk about this, we talk about from the top in the direction that we're going, or from where it starts to the bottom. So that's why it's negative. However, if on a test you tell me that it's 215.6 meters tall or high, I'm going to give you credit for it. So, but make sure that you don't leave the negative off of here, because if you leave the negative off there, your answer is going to change. But so it's okay to leave this negative off, but don't leave this negative off, because that one will change your answer. Okay, question 3. A cannonball is launched as a projectile and stays in the air for 20 seconds. If the cannonball travels a horizontal distance of 1,000 meters, what is the exit velocity? And again, when I'm asking the exit velocity, I'm not asking for the horizontal or the vertical. I'm asking for the component of both. So we want to solve for our exit velocity, and we want to solve for our angle, theta. Okay, so I want to solve for this angle, and we'll call it theta. Okay, and I want to solve for this VE here, given that we find our VIH and our VIV. So I have 20 seconds and I have my horizontal distance, so I can use that first equation to solve for my times time. So I can solve for this V horizontal by rewriting my equation to say V initial horizontal equals distance horizontal divided by time. When I plug that in, I get 1,000 meters divided by time, which is 20 seconds. And when I do that on my calculator, I get 50 meters per second. And I can just go ahead and I can plug that in right in here. So this horizontal is 50 meters per second. Okay. Then I know my time, and I know my acceleration, and I know at the very top of this curve my final velocity is going to be 0, so I can use that third equation, VFV equals VIV plus AT, right? I know this, and I know this at the halfway point, so I can solve for this. Okay, the key though to remember this is that we're halfway, so I'm going to have to think of everything in this equation as half. Okay, so my final vertical velocity at this point is going to be 0. So 0 equals my initial vertical velocity, which is what we're trying to find, plus my acceleration due to gravity, which is negative 9.8 meters per second squared, times my time that it takes to get from the initial point to the halfway point. So we don't want to use 20 seconds. We want to use half the time. So I want to use 10 seconds. So when I go to solve this, I get 0 equals VIV plus negative 98 meters per second. And then I add 98 to both sides, and I get VIV equals positive 98 meters per second. And so again, I can just go ahead and throw that over here, 98 meters per second. So now I have two sides of my triangle, and I want to solve for the third side. The way I do that is my Pythagorean theorem, a squared plus b squared equals c squared. It doesn't matter which side is my a squared, which one's my b squared. The only thing that matters is that my hypotenuse has to be the c squared side. So I'll go ahead and plug stuff in. 50 squared plus 98 squared equals c squared. And in order to get c unsquared, I have to take the square root of both sides. So c is my hypotenuse, which in this case is my exit velocity. And when I do 50 squared plus 98 squared, and I take the square root of that, I'm left with 110 meters per second. So my velocity, my exit velocity is 110 meters per second. So I'm not finished yet though. I need to find theta. Okay, theta. Okay, whenever we're solving for angles, this is where our trig functions come into play. So we can, since we know all three sides, we can use any trig function, but as discussed in class, the most useful one that will maybe allow you to not make mistakes is tangent. Because tangent is our opposite and our adjacent, which most times those are given to us, whereas our hypotenuse, in this case, we calculated. So say we messed up and we got the wrong answer for our hypotenuse, and then I go to plug it into my tangent, or I go to plug it in my trig function. If I'm using the wrong answer to solve for the next answer, then that answer is going to be wrong too. So it's just good practice to use the given answers to solve for our answer. So tangent of theta equals my opposite side, which is 98, over my adjacent side, which is 50. If I'm trying to solve for this theta, then I need to get rid of this tan, and the way to do that is take the tan inverse. So to get theta by itself, I have to take the tan inverse of 98 divided by 50. And when I do that, I should get, I believe it's 63 degrees. Let me double check that. Yeah, 63 degrees. Okay. Again, if you're getting like a decimal place, you want to make sure that your calculator is in degrees and not radians. Okay, so you should be able to look at this answer and think that that's a reasonable answer. So that's our answer for number 3. Moving on to question 4. Okay, Dude Perfect kicks a soccer ball off a cliff to make a cool trick shot that is 50 meters below. In order to hit the target, they need to kick the soccer ball with an exit velocity of 2.6 meters per second at an angle of 21 degrees. We want to know how far the target is away that they're trying to hit and how long the soccer ball will remain in the air for. Okay? This problem is a little different because we're no longer just dealing with a motion that goes up and down and finishes at the same height that it started at. We're now dealing with a projectile that's launched off of a cliff, okay, with some vertical direction. How do I redo that? So it'll go up, but then it won't land at the same height that it started from. It'll end farther down. So we still want to split this in half, but that was just god awful. Let me redo that. This pen's driving me crazy. Okay, so we want to split this in half, but as we can see, the time it takes to get to that peak is no longer the exact same time that it takes to get down from that peak. So now we're going to have to solve for our time in the first half, we're going to solve for our timer in the second half, and then we're going to add them together to get our total time that this projectile is in the air for. So the first things first, I'm just going to write my equations down off to the side so I can reference them easily. My distance vertical equals initial vertical times time plus 1/2 AT squared. And then my final vertical velocity equals my initial velocity plus AT. Okay. Again, we have our exit velocity, so I suggest the first thing you do is your trig function, because this is probably the easiest thing to do, and this is the easiest way to get some partial credit. So my exit velocity is 2.6 meters per second, and it leaves at an angle of 21 degrees. So I want to solve for my V initial in the horizontal and my V initial in the vertical. So to solve for my vertical, this is my opposite side, and this is my adjacent side. So to solve for this one, I'm going to use my sine. Sine of my angle, which is 21 degrees, is equal to my opposite side, which is my initial vertical, divided by my hypotenuse, which is 2.6 meters per second. So to solve this, multiply both sides by 2.6. And when I do that, it goes away on this side, and my initial vertical velocity that I'm left with is 2.6 times sine of 21, and I get 0.93 meters per second. That's my vertical. While we're here, let's solve for my horizontal. to do that, I'll use cosine of my angle, which is 21 degrees, equals my initial horizontal velocity, or my adjacent side divided by my hypotenuse side, which is 2.6. Multiply both sides by 2.6. Goes away over here. And I'm left with my initial velocity in the horizontal is 2.6 times cosine of 21 degrees, which is 2.4 meters per second. Okay, so now I have both of those, so now I can start plugging things in. So for my first part, I want to solve for the time that it takes to get from when it's kicked to its max height. So again, if I'm thinking in terms of halves, okay, then I'm going to use this equation here. So at the very peak, my vertical final velocity is going to be 0, equals my initial vertical velocity, which we calculate as 0.93 meters per second, plus my acceleration, which we know is negative 9.8 times time. That should be 9.8, okay, times time. To solve this, I'm going to subtract 0.93 from both sides, is equal to negative 9.8 times time, and then I'm going to divide by negative 9.8, divide by negative 9.8, and when I do that, the time that I get for this first interval is negative 0.93 divided by negative 9.8 is 0.09 seconds, so a really incredibly small amount of time. And that's going to be this first time interval here. Okay? Now we need to solve for the second time interval. And in order to do that, if I kind of look at this and I just look at this second half, I can kind of treat this second half as a problem where something's just falling off a cliff, right? It looks similar to that. But in order to solve that, I need to know the entire height at which it falls. In this problem, I only know the height of this cliff. I know that the height of this cliff is 50 meters. So in order to solve this as a horizontal projectile, I need to solve for this extra little section of height there. So the way I'm going to do that is I'm going to use this equation to solve for my distance vertical. So my distance vertical is equal to my vertical initial velocity, which is 0.93 meters per second, times the time that it takes to get to that top point, which we just calculated as 0.09 seconds, plus 1/2 my acceleration, which again, this needs to be a negative 9.8 meters per second, times my time, which is 0.09 squared. So when I do this in my calculator, 0.09 squared times negative 9.8 times 1/2 plus 0.09 times 0.93, I get that this will go an additional 0.04 meters. So it will go an additional 0.04 meters plus the 50 meters of height of the cliff. So plus that 50 meters. So the total vertical distance to the peak is going to be 50.04 meters. So now I can take that answer and I can plug it in to solve for the time that it takes to go from the peak all the way down to the bottom. And we can use that with the same equation that we did on our other problems, where we rewrote this equation to solve for our time, and we can neglect the initial vertical velocity because at this point, remember, our velocity vertical is 0. So if I'm treating it like a horizontal projectile motion problem, I can just say, oh, my vertical velocity is 0, which means that this first part of it goes away, which means that I can rewrite that equation to say that t equals the square root of 2 times my distance in my vertical divided by my acceleration. So to solve this, 2 times my vertical distance, which is 50.04 meters, divided by my acceleration. Again, don't make it negative here. This is probably the only time that you won't make it negative, because if you take the square root of a negative, your calculator's not gonna like that. So 2 times 50.04 divided by 9.8, take the square root of it. That's going to give me that the second time interval, so we can call this time 2, is going to give me 3.2 seconds. So now I take interval 1 and add it to interval 2, and the total time, so to answer part 1, how long, we get 3.2 plus 0.09, so the total amount of time that this is in the air for is 3.29 seconds. And that was the first part of this. Luckily, the second part is easy, because we can just take that answer and plug it in to this distance horizontal equation. So my distance horizontal is equal to my horizontal velocity, which is 2.4 meters per second, right? That's what we calculated here at the very beginning, times my time, which is 3.29 seconds. And when I do that, I get that the horizontal distance that this ball will go is 2.4 times 3.29, which will be a total distance of 7.9 meters. You could round that up to 8 meters. Okay, so that's how far away Dude Perfect should put their target in order to make this cool trick shot. So a lot of math to get these two answers. Okay, hopefully you were able to follow along with that. I know this was kind of all over the place, but if you watch the video, you should hopefully be able to follow each step. Okay, we'll move on to this last one. And like I mentioned in class today, this one's missing a little bit of information, and that we need to know that our initial vertical velocity is 9 meters per second. Okay, so the world's most extreme par 3 is the 19th hole at Legend Golf Resort, which sits atop South Africa's Hanglib Mountain at 400 meters tall. If the hole is 110 meters away from the tee box, and you use a pitching wedge that hits a ball an additional 30 meters high, what is the exit velocity and the angle that the golf ball should be hit to get a hole-in-one? And we're assuming air resistance is neglected. This should kind of always be implied in this Physics 1 course, that we're neglecting air resistance. But this one was, we added that information just to make sure that none of you golf pros are thinking about how the wind and everything is going to affect this shot. So I have my 3 equations. Distance in the horizontal equals velocity in the horizontal times time. Distance in the vertical equals initial vertical times time plus 1/2 at squared. Velocity final in the vertical equals velocity initial in the vertical plus acceleration times time. Those are our 3 equations. Okay, so I'm given my distance in the vertical, and let's draw a picture of this just so we know what's going on. So here's the cliff, okay, which the tee box is on top, and when you hit the golf ball, it goes an additional 30 meters tall, and it goes 110 meters to get to the hole, and the hole-in-one. So my distance is 110 in the horizontal, and my vertical distance is the 400 meter tall cliff plus the additional 30 meters that this pitching wedge hits the golf ball at. So my vertical direction is 430 meters. Okay, and so I want to know my exit velocity, which again is going to be a component of my horizontal initial and my vertical initial velocity. So we're going to want to find those two things. Okay, so the first things first, we're going to want to solve for the total time, or we can solve for this first time to get to this peak, and that gives us this time interval, and then we're going to need to solve for the other time interval. Our plan of attack, let's see. So I don't know this and I don't know that, so the first equation is not going to be a whole lot of help. I do know this. I don't know this, and I don't know time, so that first equation is not going to be a whole lot of help. So maybe the second, let's see. Yeah, the second one, because I know my distance vertical. I know my initial velocity is 9, right? Oh, so I guess never mind. We can use this bottom one here, because I forgot that I had that initial vertical velocity. So we can use that bottom one to solve for the time that it takes to get from here to the peak. Okay. When we do that, we can solve for the time, and we'll be able to, from the time, we'll be able to get our total horizontal time. Okay, so my final vertical velocity is going to be 0 at the very peak. So 0 equals my initial vertical velocity is 9 meters per second plus my negative 9.8 acceleration times my time. To solve for this, I subtract 9 from both sides, equals 9.8 times time, and then I'm going to divide by negative 9.8 to both sides. So the time that I'm going to get is negative 9 divided by negative 9.8. Negative 9 divided by negative 9.8 gives me a time of 0.92 seconds. And that's the time that it takes to get to this very top right there. So just half of our time interval, or half of, not exactly half, but you know what I'm talking about, this first half. That's how long it takes to get there. Okay. Now I want to solve for my second time interval to get the full time that this is in the air for. And this is where it's going to be kind of a little difficult, because we're going to have to use our quadratic formula most likely. So to do this, I'm going to use the second equation. So actually we're not going to have to use our quadratic, because if we're using this, we're treating it like a cliff problem, right? Which means that I no longer need to have a vertical initial velocity. So this first part goes away, and I'm left with my usual equation to solve for time, right? If I rewrite this second equation, I'll get my t equals square root of 2 times dv over a. So when I do that, I can plug this in. Square root of 2 times my vertical distance is 430 meters, divided by my acceleration is 9.8. So I get 2 times 430 gives me 860 divided by 9.8. To take the square root of that. The second time is 9.4 seconds. So the total time is this first time plus the second time. So the total time that this is in the air for is plus 0.92 is 10 seconds, or 10.3 seconds. So that's the total time. Now that I have the total time and I know the horizontal distance, I can solve for my horizontal initial velocity, and then I can solve for my exit velocity. So I take distance in the horizontal equals velocity in the horizontal times my total time. And I want to rewrite this to solve for my horizontal velocity. So my horizontal initial velocity is distance horizontal divided by time. To plug this in, my horizontal distance is 110 meters. My time is 10.3 seconds. Therefore, my velocity is 10.7 meters per second. So now I can finish off my exit velocity triangle. And I know that my initial vertical was 9 meters per second. I know my initial horizontal, we just calculated as 10.7 meters per second. So now again, the same way we did earlier to calculate the third side of a triangle, a squared plus b squared equals c squared. So I can do 10.7 squared plus 9 squared equals c squared, right? So 10.7 squared plus 9 squared, take the square root. My exit velocity exit equals 13.9 meters per second, or you can round that up to 10. So this golf ball needs to be hit at 13.9 meters per second in order to get a hole in one. And it needs to be hit at a specific angle, right? If I can't just hit this 14 meters per second at any angle, it needs to be specific to this angle. So how are we going to find that? Just like we did earlier, tangent of theta equals my opposite over my adjacent. Okay, when I need to solve for theta, I'll do the tan inverse. So tan inverse of opposite over adjacent. So 9 divided by 10.7. Take the inverse of that. And this golf ball needs to be hit at an angle of 40 degrees. So to get a hole in one on this really cool 19th par 3, the highest in the world or the most extreme, you need to hit your golf ball at 14 meters per second at a 40 degree angle. And if you're lucky and there's no air resistance or not a whole lot of wind that day, you might be able to hit a hole in one. All right, this video was kind of long. This last problem was extremely long. You should expect on your test maybe a problem that's closer to number 4, and maybe probably just one of those. So, but you should still get familiar with it, and it's not a whole lot harder than the other ones. It's just more steps and more time consuming, which allows opportunities for you to mess up, which I guess can make the problem harder. But if you follow along with the steps and you kind of just check each of your equations and mark off, okay, I can use this one, I can't use this one, and just follow those steps, you should be all right. Again, like I said in the last video, if you have any questions, make sure you come talk to me before or after school, and we'll hopefully get those ironed out and get you ready to do well in this exam. All right, we'll see you guys at the next video.